These are the limiting reactant notes. It'll be helpful to have a periodic table and a calculator available. To start these notes, we completed a gram-to-gram entrance question. So if you can pause the video and try these 2 gram-to-gram stoichiometry problems on your own, that would be great. We are going to come back to these answers later on. All right, so what is a limiting reactant or an excess reactant? Well, we're going to talk about what those are, but kind of looking at an example of visual identifying the limiting or the excess reactant. So if you are throwing a barbecue and serving hot dogs, each hot dog requires a bun. So this would be an example of something with a 1-to-1 ratio. So if you have 5 hot dogs and 4 buns, the buns will get used up, which makes the buns limiting, and you will have 1 hot dog left over, which would make those hot dogs excess. And so if we are looking at visually identifying, we would see that 1 hot dog that is left over because it couldn't be eaten without a bun. If you instead have 5 hot dogs and 8 buns, the hot dogs get used up, so you're able to make 5 hot dogs with buns, and you will have 3 buns left over, meaning those would be your excess. So we would see those 3 buns that are left over that couldn't be eaten without a hot dog. And so as we're thinking of a reaction, reminder that in a reaction, our reactants are on the left, the things that we have at the start. Our products are on the right. And so when we're talking about limiting or excess reactants, we are talking about those chemicals to the left of our arrow that we are starting with. In this case, that would be the hot dog and the bun separated or separately. If we start to look at this in terms of a chemistry example, here we have some pictures of those different molecules for this reaction. So nitrogen gas reacts with hydrogen gas to produce ammonia. So this is our reaction here. My nitrogen gas is one of my reactants. My hydrogen gas is also one of my reactants. Ammonia is our product. If you have 3 moles of nitrogen, so before the reaction, we have 3 moles of nitrogen. Those are the green, are 3 moles. We see those in pairs because nitrogen is diatomic. And 6 moles of hydrogen. That hydrogen, we have 3 moles of those H2, or 6 moles of the H2, sorry, with that. What is our limiting reactant? Well, if we look, each ammonia requires 1 nitrogen and 3 hydrogens. So those are our groupings that we see here. Those NH3, these are those groups. And we get out 4 moles of that NH3, but we still have, after that reaction, we have a mole of N2 that is left over because we ran out of our hydrogen. So our limiting reactant is hydrogen because it is all used up in forming product. The reactant that still remains after the reaction has stopped, well, we still have nitrogen left over, and so that nitrogen, or N2, is our excess reactant. And we can see our excess reactant because there is nothing left for it to react. It is difficult in a lot of reactions for us to actually see the differences in our chemicals, but on a molecular level, this is what is happening. If we kind of look at 2 more, feel free to pause the video and try this on your own. The reminder, the limiting reactant gets used up, so we will not see any of it left over after the reaction is complete. And that means we won't have any of it in its original form. Excess reactant won't get used up, so some of it will still be visible in its original form after that reaction is complete. So looking at these 2 examples, we have a before and after. We don't know what these chemicals are. Let's just talk about that in terms of blue and pink. So my limiting reactant, I'm going to look after and look at what got all used up in pairing. And that those blue reactants all paired up, but our excess, we still have some pink that are left over and that didn't have anything to react with. And so we see some of those pink in their original form that haven't changed. Looking at this next kind of visual example where we have hydrogens and oxygens, seeing here are our reactants on the left, so looking for those in the original form. Our products here, we are able to form products, but then we run out of oxygens. So oxygen is our limiting reactant. If you were just going to write oxygen by itself, it would have to be O2 because it's diatomic. And then our excess is those hydrogens, or H2, because those were all alone and didn't have any oxygens left to react with. We are going to do a lab where you're going to be able to look at different chemicals, and you'll be able to visually see your excess reactant. Often there aren't reactions we can do in class that allow us to see this, so I picked this example just for us to kind of model, even though it's not something we could do in class. So if we look at this example, we have C2O4H2, a colorless solution, and KMNO4, a purple solution, that are going to react. So notice here are our reactants. This is colorless. This is purple. Aqueous, we see that those are solutions. MnO2 is a black solid, and so that's one of our products. That's a black solid, and then let's assume all other products are colorless. And so these are going to be colorless as we look at our products. And so we're now asked to sketch what the products would look like if we have each of our reactants being limiting. Let's first just start by looking at, well, what would we have, what gets produced, and how could we model that? I'm going to start with, we've got a black solid. So I'm going to just put some solid maybe at the bottom here, and I'm going to just label this as MnO2, just so I know what that is. Then looking at what else I have aqueous and liquid, and so let's just show that there's some water there. If you want, you can kind of show that this is solid down here. But we have some K2CO3, and we have H2O in that reaction, or in our beaker. If you wanted to, you could kind of show some bubbles of CO2 gas leaving, but really we don't necessarily need to show that. So there's our CO2 gas, and then we have, this is going to be a colorless solution. So if everything gets used up, this is what we should end up seeing after our reaction. But we know that we are going to have something that is limiting, and so that is going to change what this might look like. But if everything gets used up, these should look the same. We should see a black solid, and then colorless liquid and colorless gas. So sketch what the product would look like if C2O4H2 is limiting. So if we use up all of this colorless solution, that means that we would have KMNO4 excess or left over, meaning that we would see that KMNO4 left in our beaker. And so I'm going to see some of this KMNO4, so I'm going to add that into the beaker because that's there as well. And since if you're doing this on your iPad, we can easily just go ahead and add in and say, okay, well, this would actually not be a colorless solution anymore. It's going to have some tinge of purple depending on how much of that KMNO4 is left. If we're looking now at B, sketch what the product would look like if KMNO4 is limiting. Well, if we run out of our KMNO4, this purple solution, that means we're going to have excess of our C2O4H2 is going to be excess, and so we would be able to see that at our in our beaker. And so we would also, you're not obviously going to be able to actually see how these are different in the beaker. They would be all mixed together. but we would still have that colorless solution because all of these things in here are colorless, so this would remain a colorless solution in your beaker. So if we have distinct colors, we can see some of that excess reactant, and we could use that visual to identify what is limiting and what is excess based on our knowledge of what each of these look like. All right, switching over to our kind of mathematical, how do we do these calculations? So remember that gram to gram entrance question. We were given some values for this reaction. So my answers for this gram to gram entrance question below, we were given 4.56 grams of aluminum. So we did that, grams of aluminum, to figure out how much hydrogen that produced. And that produced 5.11 grams of hydrogen. So we got 5.11 grams of hydrogen from our 45.6 grams of aluminum. That second problem asked us how many grams did we get from our sulfuric acid. So from those 5.93 grams of sulfuric acid, we got 1.224 grams of hydrogen. So we did those two calculations where we were starting with our two different our values for each of our reactants, and in both of those we found, okay, how much hydrogen for each. Now as we look at these, which reactant, aluminum or H2SO4 sulfuric acid, produced less hydrogen? This is a smaller number, so that means that our H2SO4 produced less hydrogen, which makes that our limiting reactant. Another name for that is limiting reagent. We're not going to actually discuss using that term reagent, but you might see that if you are looking for help elsewhere. And again, our formal definition for that limiting reactant. It is the reactant, again, our reactants are on the left, in the reaction that limits the amount of product that can be produced. So we could only make 1.224 grams of hydrogen because then we are going to run out of one of our reactants and our reaction is going to have to stop. Which product produced more? Well, our aluminum produced more, which means that that was our excess reactant. It could produce 5.11 grams of hydrogen, but it's going to stop producing after this much because our H2SO4 is running out. And again, our definition for excess reactant, the reactant or reactants, if there are multiple in a chemical reaction, that are excess or remaining after the reaction is complete. So now if I want to determine the limiting reactant using stoichiometry, you're going to need to complete a conversion of both given amounts, so whether we're given grams or moles, of each of our reactant to the stated product. So this one asked how much hydrogen was produced, so we did aluminum to hydrogen and sulfuric acid, H2SO4 to hydrogen. I could have easily asked us to figure out how much of that aluminum sulfate, but it will be stated which one it is asking you to produce. So we do each of those stoichiometry calculations to the same product, and then we compare. The reactant that made less product is limiting. The reactant that made more product is going to be our excess reactant. All right, so if we look at this example, if you react 140.5 grams of zinc with 90.5 grams of phosphorus to produce zinc 2-phosphide, given the following equation and calculations, what would be the limiting reactant? So we have our balanced chemical reaction here, which is necessary for stoichiometry. We're taking each of those given values and doing a calculation. So I have each of these starting values I was provided, and we are figuring out how much zinc phosphide will each produce. So that zinc produced 185.2 grams of zinc phosphide. Our phosphorus produced 375.1 grams of zinc phosphide. So what would be the limiting reactant? Well, we're at that comparison step because we have the work. The reactant that made less is going to be limiting. And so because that 185.2 grams is a smaller number. That makes zinc, the reactant that produced that, our limiting reactant. That then also means this is the maximum amount of zinc phosphide that could be produced. And we also call this our theoretical yield. Because in theory, if you were to go through and do a reaction, there were no mistakes, no error, that is theoretically how much you would be able to produce. Here is kind of a compilation of our definitions for this section. We talked about that limiting and excess reactant, that theoretical yield, again, the amount of product calculated. So we're doing that stoichiometry. Using the balanced chemical equation, the maximum amount of product you can make with the amounts available, which is limited by our limiting reactant. So that's our definition of theoretical yield. We've also talked about that in lab. We also might be provided an experimental yield. This is the amount of product that was actually produced, whether that was through lab data. So you might have an experimental yield if you are completing a lab in class, or it may be provided in a question. And we can use that theoretical yield and the experimental yield to find the percent yield as well. So we're going to do a problem with that percent yield coming up. And then we have one more thing to kind of add on before you're done. Feel free to take a minute and write out this balanced chemical equation on your own. It asks you to do that. I already have that provided for us, and I put a 2 in front of our sodium chloride in order to balance that chemical reaction. Reach out to your teacher if you have any questions on doing that. Part B then says, what is the maximum number of grams of calcium carbonate that can be formed? So we were told that we have 1.2 grams of our calcium chloride. So our first thing we're going to have to do is figure out, well, with that calcium chloride, how much product can be produced. So that 1.2 grams of calcium chloride, and we are starting with 1.5 gram solution of sodium carbonate. So starting here as well. And we have 2 problems, each with those the starting values that were provided from our problem. And then our problem asks us, these are reacting to produce calcium carbonate and sodium chloride. What is the maximum amount of calcium carbonate that can be produced? So each of these are going to end at that same value, us figuring out how much calcium carbonate is needed. So I'm going to go through and do the work for this first problem for us. And then I'm going to, just as a refresher of our stoichiometry, so we have 1.2 grams of that CaCl2. In order to switch to calcium carbonate, I need to get to moles, and so I know that 1 mole of CaCl2 is the molar mass in grams of CaCl2. I can go to my periodic table and add that up. 1 calcium and 2 chlorine, that molar mass is 110.98 grams. Now, my next step is I need to go from the moles of CaCl2 to moles of CaCO3, which is what the problem is asking me to get to. For this, I use my coefficients from my balanced reaction. I have 1 mole of CaCO3 and 1 mole of that CaCl2, so that's a 1-to-1 mole ratio. And then I need to, because this asked for grams, I need to get back to grams of calcium carbonate. And so we know 1 mole of CaCO3 is going to equal its molar mass. That molar mass is going to go on the top. If I go to my periodic table, 1 calcium, 1 carbon, 3 oxygens, 100.086 grams of CaCO3. And then I can go through, do that calculation, and I get 1.1 grams of CaCO3. I'm leaving 2 sig figs because I have 2 sig figs here. And then my molar masses, this is 5 sig figs and 6 sig figs. My mole ratio, those don't have sig figs because those are exact. Same thing with in our 1 moles in our conversions. So 2 sig figs is my answer. So I did that for the first value I was given for my first reactant of that calcium chloride. My second step is to do the same thing. with my sodium carbonate, but now an ending with that calcium carbonate. Feel free to pause the video and try that on your own, but there is my work, and I ended with 1.4 grams of CaCO3. So I've done both of those problems. Now I need to compare. Which of these made less? Which of them is going to run out first? And 1.1 is a smaller number, which means that this one is the maximum amount that can be produced. Because after that much is produced, our calcium chloride, CaCl2, this is our limiting reactant. It is going to run out. We don't have enough of that to use up all of that Na2CO3, which makes that our excess reactant in this case. All right, going on to part C. If you produced 0.85 grams in a lab, what is your percent yield for this reaction? So in a lab, that's going to be our experimental yield. The theoretical yield is what we just found in our last problem. So we can find that percent yield by doing our 0.85 grams. And again, this is grams of that CaCO3 over our 1.1 grams, which is the maximum that we can be, is able to be produced. And we are going to go ahead and, nope, not like that, and divide by that 1.1 grams of CaCO3, and then multiply times 100 to get that percent yield. We are going to use sig figs here because we have, we're not doing percent composition. This has 2 sig figs. This has 2 sig figs, so 0.85 divided by 1.1 gives me 0.7727 times 100 to get that decimal to a percent. I have 77.27, leaving 2 sig figs, that's going to be 77%, is that percent yield. All right, part D, how many grams of the excess reactant is left over? So remember, our excess reactant is that Na2CO3, and we have some of that is left over. So we are starting with, from our problem, 1.5 grams of Na2CO3, but we know that we have excess, so we don't know how many grams of Na2CO3 are going to be left at the end. So we need to figure out how much was used. And so we need to look at something that we know is completely used up. We know we used up all of this 1.2 grams of calcium chloride. So let's figure out if we have 1.2 grams of calcium chloride. Let's see how many grams of sodium carbonate is going to be required for us to do that. So this is going to be another stoich problem. We have 1.2 grams of CaCl2. We need to go from grams to moles. We already had that molar mass from when we did our initial stoich. Now I need my mole ratio. 1 mole of Na2CO3 to 1 mole of CaCl2. And then going from my moles of Na2CO3, 2 grams, 105.998 grams of Na2CO3. So I'm figuring out how much of my excess reactant is actually going to get used up from that limiting reactant. And I get 1.1 grams of Na2CO3. That's how much actually gets used in the process of my reaction. So if I am starting with 1.5 grams, I use 1.1 grams, how much is going to be left over? Well, let's take that 1.5 grams of Na2CO3 that we started with. Let's subtract off how much got used, and then we can figure out our excess. So 1.5 minus 1.1, so 0.4 grams. We just have one digit after the decimal because of our subtraction rules of Na2CO3 is going to be left over, or would actually be that amount of our excess. Last part here says sketch a model of the reactants and products that would be present after the reaction. We don't actually know anything about what these look like, but if I'm looking, all of these are aqueous, so I'm going to just draw some water here. At the end of my reaction, I'm going to have that calcium carbonate and that sodium chloride. So I'm going to draw those in there, CaCO3, NaCl. I'm going to actually put two NaCl's in there because there's 2 moles of NaCl here. But we also know that we have some of this Na2CO3 left over. And so let's also put that in there. Na2CO3, and we'll put that in there to show that we had some of that left that didn't get completely used up. All right. The next problem, feel free to go ahead and try this on your own. I'm going to just talk through it. I'm not going to do all of the calculations. There is a reaction for us to write. 2.5 moles of carbon tetrahydride gas burns with 1.9 moles of oxygen gas to produce carbon dioxide and water. So here we get our reaction. Our gases, oxygen's diatomic because it's an O2. You may not have included this triangle. That is indicating that something burns. If you left it off, it doesn't actually change your problem. So we have our balanced reaction. What is the maximum number of moles of water that can be formed? So this one is just asking us for moles, so we don't actually have to go all the way to grams. We're still, though, going to have 2 problems. We're going to have one problem where we're starting with our moles of carbon tetrahydride and ending with our moles of water, because that is what the problem asked us for. Our second problem then is going to be starting with those moles of oxygen gas that were provided and ending at that same spot. So now we're again starting with moles of oxygen gas and ending at the same spot with that H2O. If you want, take a minute to go ahead and do those calculations. I've got that work for us here. So from both of those, my 2.5 moles of CH4 produced 5.0 moles of H2O. My 1.9 moles of O2 produced 1.9 moles of H2O. So what is the maximum amount that can be formed? Well, whatever is smallest is the maximum amount that can be produced. So this is our theoretical yield, or the maximum amount that can be produced. Our oxygen, in this case, is our limiting reactant. It's going to run out first. That makes our CH4 our excess reactant. Moving on to find that percent yield, if you actually produced 1.7 moles of water, so let's say we did an experiment, what was your percent yield? Well, this is our experimental yield, 1.7 moles of H2O. We're going to divide that by, well, the maximum we could produce is that 1.9 from our last problem. Divide and multiply by 100. Both of our starting values have 2 sig figs, so 89% would be our percent yield. All right, that last step, how many moles of your excess reactant are left over? So our excess reactant is CH4. We started with 2.5 moles of CH4. We now need to look at how much did we end with. So we don't know how many moles we're ending with. That's our excess. So let's figure out how many moles of that CH4 were used. In order to do that, we have to know an amount that got totally used up. So we know our limiting reactant was that oxygen. I know my limiting reactant gets completely used. So my limiting reactant is that oxygen. So let's figure out, if we're using that, how many moles of CH4 is required to complete that reaction. We know it's less than 2.5. And so this is just going to be a one step because it's mole to mole. 1.9 moles of oxygen, getting rid of moles of oxygen, getting to moles of CH4. We use our coefficients. So we have 1 mole of CH4 and 2 moles of oxygen. So 1 and 2. And then we can go through and do that math. And we get 0.95 moles of CH4. That's how much is used. So if we want to figure out how much is left over, well, we started with 2.5 moles. We are using 0.95 moles, so we can subtract those, and we're going to get 1.6 moles of that CH4 are left over. All right, that is the end of these notes. There's practice available in the form of a worksheet. There's also a check-in posted for you on Schoology. Reach out to your teacher with any questions.